Us humans rely a lot on electricity in our everyday lives, and for most it is something we cannot live without. Since 1882, the main ways of producing energy are at coal power plants. However, this has a negative effect on our environment, so we have been looking for alternative ways to create energy. One popular method is harnessing the power of air, using wind turbines to generate this electricity. We designed a horizontal axis wind turbine that would rotate in a clockwise manner when viewed from the wind direction. We designed such that the maximum angular velocity shall not exceed 3000 rpm, and the maximum power coefficient that must also be obtained at a tip-speed ratio between 3 and 8. The prototype we manufactured as a single part and must be able to be printed in a box 400mm in length, 75mm in depth, and 150mm in height. We incorporated an original design feature to help improve the performance of.
During the R&D stage, the essential decision had to be made on the number of blades for the turbine. A single-bladed design can lead to difficulties with balance of the blade, ultimately resonance and destruction. Three-bladed design increases solidity, but it doesn't utilize most of the printing space and reduces the size of the turbine. With compromises to both size of the turbine and easiness to balance it, we agreed on the design of the two-bladed turbine. An internal folding mechanism is designed within the nose cone to utilize most of the printing space while ensuring a clean surface after the turbine's assembly, and the contact surfaces between the two blades are roughened by adding grooves for an accurate and secure glue bonding. Flow separation was also found on the upper surface of the aerofoil near the roots of the blade. Therefore, devices have been added to the root section. This flow device, inspired by shaft skin, reduces drag by forcing the boundary layer into turbulent regime, which allows the boundary layer to stay attached against great adverse pressure gradients.
When considering the aerodynamics of the wind turbine, there are two important factors. The power coefficient is actually the power extracted by the wind turbine divided by the maximum theoretical power that could be extracted from the air. And we are interested in predicting Cp max. The second factor is the tip speed ratio. The tip speed ratio is actually equal to the tangential velocity of the tip of the blade over the wind speed. Too low, and most of the oncoming flow goes through without extracting power. Too high will lead to higher blockage effects as the turbine approaches an idealized disk with too much drag. Hence, there exists an optimal TSR, and our job is to predict that TSR. Furthermore, the choice of the blade profile is really important. Our two main candidates were the SG6043 and the SG6040, which are both optimized for wind turbines in low Reynolds number flow. As we can see from the curves, the SG6040 has a slightly lower lift and drag coefficients, but it is much more structurally sound. This alleviated the failure risk. Having chosen the blade profile, we now need to consider that the rotational speed increases as we move away from the center of the turbine to the tip, while the wind speed remains the same, meaning that the relative wind speed increases as we go along the blade and its direction varies. This translates to a change in area of the profile and twist along the blade to ensure the optimum angle of attack all along the blade. These variations were determined using a modified Schmitz model which accounted for blockage and weight losses.
For structural analysis, we have taken each blade as multiple longitudinal sections to calculate the forces experienced at different radius to confirm if the design is strong enough to maximize the aerodynamic performance, yet remain reasonably rigid under the 12 meter per second wind speed. Tip speed ratio of the wind turbine is moderated with Q blade. Further fluid structure interaction simulation in ANSYS reveal a Cp max of 0.334 with this tip speed ratio, which through the estimated tip speed ratio, we were able to calculate the angular velocity of the blades, leading to the velocity of each section of the blades. The velocity of the air over the airfoil were then calculated using the velocities of the sections of the blades and the incoming air. The aforementioned quantity leads us to the coefficients of lift and drag. The force and moment experienced by each section could then be calculated. The second moment of inertia was then estimated using an elliptical profile. The stress at each section was then calculated. Thirdly, the centrifugal force each section experienced was calculated using the angular velocity of the blades and reckoning that each section was accounted for the mass of all the outer sections. Further, ANSYS simulation shows a 0.3 cm wind tip deflection, which is well under value.
After the design phase, we began prototyping the wind turbine. The hub was machined based on our Creo drawings in 4 steps. The aluminum cylinder was trimmed by turning. A hole was drilled through the center. The cylinder was then milled to obtain smooth corners and edges. Finally, a keyhole was added onto the hub by broaching. Due to time constraints, the wind turbine itself was produced in one part using rapid prototyping via additive manufacturing. We 3D printed our turbine based on our Creo model. The material used for 3D printing was ABS plastic. During printing, it was discovered by the NEP technicians that the mechanism holding the two halves together had broken off. Therefore, we decided to discard the link and pin mechanism since the turbine would be held strongly enough by epoxy alone. After printing, the two halves of the turbine were fused together using hot melt adhesive glue gun, and extra adhesive was sanded off. The turbine surfaces, trailing edge and leading edge, were then sanded manually to achieve the desired surface finish.
Then came testing. The wind turbine was mounted in a testing rig in the Donald Campbell wind tunnel. The wind speed, which was adjusted indirectly by setting the fan voltage, was measured by a pitot tube downstream and was initially set to 14 meters per second to get the model to free spin, and then set to 6 meters per second for the first test. Once the turbine had reached its steady maximum RPM, a magnetic brake was applied to obtain the minimum RPM at stall. Then the turbine was again allowed to free spin, and the brake was used to apply controlled deceleration, while torque and RPM were recorded and plotted live. The test was repeated at 8, 10 and 12 meters per second wind speed. At higher wind speeds, we noted that the turbine free spin RPM far exceeded what we expected. Some resonance and flutter effects were also noted as the turbine began to cause audible vibrations, which attenuated in volume after a certain RPM range. Furthermore, this testing method may have introduced some inertial effects due to the deceleration of the motor shaft, and so this wasn't constant. As predicted, the power output rose with increasing wind speed. Our maximum power output was 142.5 watts at an angular velocity of 2,889 RPM. This translates to a CP of 0.442, as normalized by the 0.629 meter diameter, and a TSR of 7.9. This is a relatively good power output at approximately 75% of the BETS limit, which, according to Burton et al., is close to the best performance of real wind turbines. However, we must concede that the relatively large tunnel effects such as blockage must influence this result due to the relatively large rotor disk area with respect to the wind tunnel area. The result TSR is also around 30% higher than our design of 6.2 due to the same tunnel effect. The quality of 3D print could be improved by using a CAD technique called matrix modeling. This is when the blade's geometry is defined as a matrix of coordinates, rather than as a vector sweep from the discretized section. By doing this, we can achieve a more accurately defined leading and trailing edge, which would theoretically give us more lift and hence a better CP. Additionally, we may have been able to print a larger blade within the constraints of the box by reorientating the hinge to allow us to print along the diagonal axis, but this would also require a redesign of the nose cone.